All right, so everyone, for the next talk, we have Niven Achenjang from Harvard.
Sure. We're kind of in between schools right now.
In between institutions, to talk about local duality.
Thanks for the introduction. Thanks everyone for being here. So, main point today is to get to some description of some duality statements that exist in the cohomology of local fields. So as a warm-up, let's start with nice familiar ground, and let's talk about finite fields and their cohomology. I should also say at the outset that I very much welcome questions and interruptions when I give talks, so don't be shy, feel free to speak up. Alright, so F is going to be some finite field with two elements. We want to talk about the cohomology of this field, which I mean it's Galois cohomology. So maybe let me just remind everyone what its absolute Galois group is. So for E over F, some finite extension, say of degree n. I guess we know that the unit here is a group of order q to the n minus 1. So if you remember back to your group theory days, Lagrange's theorem will tell you that every element of this group satisfies x equals to the q to the n minus 1 equals 0. So anyways, have an element, you raise it to the order of the group, you get the trivial element. And so if you want a polynomial that 0 also satisfies, you can multiply 2 by x. So finite extension degree n, all its elements will satisfy this polynomial. And so we get the fact, probably familiar the most. If you have a finite field and you take some degree n extension, then what you get is always going to be the splitting field of this nice separable polynomial. And so one of the things about this a bit, then from this sort of description, you can recognize that E over F is Galois, and furthermore, its Galois group is Z1 and Z. The generator here is what people call the Frobenius monomorphism. Generated by the map, it just takes something and raises it to the cubed power. You do this n times, and you end up back at x where you started with. Alright, so this is, finish that up. Okay, so this is description. Every finite extension of a finite field, they're all Galois. Galois group is always Z1 and Z. And so if you look at, so whenever I write G sub a field, I always mean its absolute Galois group. So this thing, by definition, is the inverse limit of the Galois groups of all the finite extensions, and we've just said that that's a bunch of Z mod n's. So the absolute Galois group of any finite field is Z hat. That's sort of like pro-finite completion of the integers. Okay, I guess I'm only writing a path for this. Okay, so trying to study the Galois cohomology of finite fields. We have our Galois group. Maybe the next step is to start saying the word cohomology. So just as a bit of notation, let me write a little few fewer characters on this board. If F is a field, I'll write Hn of F comma blah to really mean like the cohomology of its absolute Galois group. It just, cuts out 20 G's from the talk. So yeah, anyways, imagine most of this was familiar to most people here, but if this wasn't familiar to anyone and it was like, too quick or anything, let me know. But if not, I'll continue. Alright, so do some computations. So for M, any torsion GF module, so more or less any GF module, it's not often you see non-torsion ones, but for some Galois module for your field, its first cohomology group turns out to be rather explicit. It's M, but you mod out by the action of Frobenius minus 1. So you kill any element that looks like Frobenius times M minus M. So this thing where you mod out by Frobenius minus 1, this is what people call the Frobenius co-invariance of your module. So I won't give a full proof of this. I won't give a full proof of anything during this talk, but I'll sketch a few things. So H1, so Galois is our Galois cohomology group. All right, Z1, for the group of 1 cocycles. V from GF to M. So recall being a 1 cocycle means that if you take G times H, you have this cross-through twisted homomorphism property. Normally you'd expect V of G plus V of H, but on the second factor there's an extra action by this element G. And the main claim the main claim that goes with this is that there's a map there's a natural map that just takes a 1 cocycle and evaluates it at Frobenius. The main thing one wants to do to prove this proposition is show that this map at the level of cocycles is an isomorphism. So injectivity is not that hard to see. These are maps out of GF, which we've just said. There's some procyclic group. So any map is determined by where the generator goes. Look at that. We're recording where the generator goes. So this is injective. Surjectivity takes a little bit of thinking, and this is where you actually need to use that this module is torsion. And it's also the reason I'm not giving it full proof. Morally, what you do is you choose some element here, gets killed by some number n. So you use that, and then you use the fact that this is the action of GF is continuous, so that it has some stabilizer. That's some finite index subgroup. And then you have to like use both the n and the n torsion and like the index of this subgroup together to construct a 1 cosine. And so if you ask me afterwards, I can like write down the full thing, but for the purpose of this talk, it didn't seem to be the most important thing. Alright, so we accept that this is an isomorphism. And now you take quotients. So here, H1 is this C1 mod out by co-boundaries. Here the C1 we've just said is isomorphic to M, and if you think about it, the co-boundaries get mapped exactly to things of the form Frobenius times x minus x. You know, co-boundary is exactly a map where you choose some element x, and then phi of that thing is that thing times x minus x. I'd say it computes H1 of any Galois module over a finite field. And if we can do H1, why stop there? So if you look at the higher homology groups, these all vanish. So in words, one would say that that Z hat, or maybe F, whichever one you want to center, has cohomological dimension 1. This is the statement that like cohomology groups vanish in degrees 2 and above, but not necessarily in degree 1 for these torsion modules. Yeah, so for anyone who hasn't seen this wave argument before, the strategy I'm going to sketch here is what's known as dimension shifting. So there'll be lots of unjustified claims, but take my word for it. So the starting point is to consider this module, the induction from 1 to G of M, which is just a fancy way of saying you consider continuous maps. Not necessarily homomorphisms, just like set theoretic maps from G into M. This inherits this G should be a GF. This inherits some Galois action. Anyways, I guess from the action on GF. And so this. Okay, and I won't show it here, but it's not too hard to show that this thing is acyclic. By which I mean M that all its higher homology vanishes, starting at 1. So now once you have this, you can play the following game. Where there's some embedding from M into this induced module. Or what does this do? You have some element here, and you need to produce a map. So you might as well just produce the constant map. So as one can check that this is an embedding. It's even Galois equivariant. And then I'll just write M prime for whatever the quotient this embedding happens to be. you have this short exact sequence. It induces some long exact sequence in cohomology. But this thing's higher cohomology all vanishes. So the H1 here is trivial, and the H2 here is also trivial. And in between that, there's an H1 here and an H2 here. H2 will be the same as H1 of Fm prime. And this, we just computed over there, M prime modulo Frobenius minus 1. And now we have the following nice thing. This is some quotient of M prime. M prime is some quotient of this induced thing. So this is also a quotient of like the corresponding quotient of this induced thing. Yeah, and like, there, to say that in symbols instead of words. This is a quotient of like the same expression, where you replace M prime by this induced thing. Just because it was already a quotient before you mod it out by Prob minus 1. Then we apply that fact the second time. You see that this is H1 of the induced H1F, comma this induced thing. And then we apply this acyclicity fact again. Say that this is 0. So this H2. This H2 is isomorphic to some quotient of 0. Exercise for the listener. There's only one quotient of 0. So what this shows, yeah, maybe since I'm on the board space, I'll say the rest of the arguments just in words. So this shows that H2 of Fm is 0. It shows this not just for M here, which is some arbitrary torsion thing. So it shows this for any torsion thing. So not only is H2 of Fm 0, but H2 of Fm prime is 0. Because M here could have been anything, so plug M prime in there. But now this exact sequence, this thing's H2 and H3 vanish. H2 of M prime is the same as H3 of M. We just said H2 of M prime is 0, so H3 of M is 0. But M could be anything. So H3 of M prime is also 0, and just keep going like that. So what's used for an eraser?
They're both fine, yeah.
Alright. Actually, it doesn't matter. Because there are more boards. Yeah, so let me check time. Okay, yeah, so let me just say two more things about finite fields, and then we'll get to the meat of things. So we just computed all the Galois cohomology of finite fields, and one nice way of packaging these two previous statements is to say that you have some exact sequence. H naught is always invariant. So because your group is generated by Frobenius, invariants are just invariants of Frobenius, kernel of this map. And then funnily enough, we just said that H1 was the co-kernel of this map. This one sequence will help you remember what the cohomology groups are. And they change advantages for n at least 2. In the spirit of duality statements, another thing you can get as an output of this computation is that for such n, let's say M dual in this finite field context. It's just going to be homomorphisms like of a billion groups from M into Q mod Z. Okay, this inherits some Galois action. Then, okay, yeah. And then for all n, there's the following, let's say like one-dimensional duality type statement, by which it means there's some perfect pairing between the cohomology of M and the cohomology of M dual, but in this regime where the numbers add to 1. And it lands in say the H1 of Q mod Z. But here, yes, we computed H1s. Okay, there it is. Here, this H1 is just going to end up being Q mod Z. Like there was some like mod by Frobenius -1, but this Q mod Z has trivial Frobenius action. So Frobenius -1 is 0. Yeah, so there's some. Yeah, so that the theorem is that if you look at the cohomology of M and then the cohomology of its dual to some like rearranging of numbers, then the two are like exactly dual to each other. There's some perfect pairing here. Yeah, so for n at least 2, this is easy because both of these things are just 0. So that much is clear. But for n equals 0 or 1, this is also less scary than it looks. And essentially what this says, if you unpack things, or if you take Frobenius invariance, and then that's what's the dual of this. You look at the dual of M, and then you take Frobenius co-invariance. And like a similar statement the other way around. So I guess should be, if you take Frobenius co-invariance, and that's what's the dual of that, then it's, you look at the dual of M, and you take Frobenius invariance. And hopefully these look like the sort of statements that one could like prove by hand if they really sat down and thought about it for a while. But yeah, so this is.
Is the M superscript prop, is that what points it in the fixed about Frobenius?
Yeah.
That's the fixed one.
Yeah, so M superscript, yeah, it's the Frobenius invariance, yeah.
What about the subscript?
This is these, maybe I erased it. There we go. Oh, that's right there, nice. These are these co-invariants. So it's sort of like, instead of the biggest subgroup where Frobenius is trivial, it's like the biggest quotient where Frobenius is trivial. Anything else before I go on? Maybe not one. I'm just going to start erasing at this point. Yeah, why not? Okay, so this has been Galois theory and cohomology of finite fields. So in the next hardest step, is to think about local fields. So fix a prime P. And then we'll also fix some p-adic field, so some finite extension of QP. And now, so if reminiscent of this, we want to say that there's some similar duality in the cohomology of this field. So it will now be a two-dimensional duality, so this one's going to be a 2 whenever I get to the statement. But first, let me just remind you that local fields are related to finite fields. Let me take for granted that you know this actually. Let me do something else. So I want to write KUR for the maximal unramified extension, however you spell this word, for the maximal unramified extension of K. And so what this means is that we have some tower fields where we have K, we have its maximal unramified extension. This is going to be Galois, and it's Galois group U. Right. F, or if I want to be more specific, which I don't think I want to be ever, I'm just write F is now the residue field. Okay. So it's some finite field. So this is some Galois extension. Its Galois group is isomorphic to that of the residue field, so some copy of Z hat. If we look over here at the big side, then we get the absolute Galois group of K. And then the group showing up here, this is what I'll define to be the inertia subgroup of GK. And so, you group theoretically instead of field theoretically. This is just saying that there's some exact sequence where inertia sits inside of GK and the quotient is GF or Z hat, depending on how you like to phrase things. So this allows one to make the following definition. So this thing of local field. We'll define unramified cohomology to be the following kernel. Which maybe because I like exact sequence, I'll write like this. So the nth unramified cohomology group of K acting on some module, A sub GK acting on some module, is going to be the kernel of the map where you can take normal cohomology of K, and this restricts to cohomology of K unramified. So any class that's killed when you pass the maximal unramified extension, we'll say is an unramified class. Let me also just note, in case you like groups more than fields, this thing is the cohomology of the inertia group, and this is cohomology of the absolute Galois group. I think I'm too confused by how these boards move, so I'm just gonna erase as I go on from now on. So yes, I guess a general theme of working with local fields is that no matter what you're doing, you're going to want to define some unramified version of it. So here's the unramified version of cohomology, and here, let me do a remark and then a quick example. So if n is equal to 1, you can be very explicit about what this group is. is going to be is the following expression. So maybe one way to think about this is that H1 is supposed to be cohomology classes. So H1 and ramified is supposed to be cohomology classes that die when you restrict to inertia. So maybe you should think that that means that they're really coming from cohomology of GK mod inertia. So anyways, one can sort of like define this map by hand and just check that there's an isomorphism. Or if you know the inflation restriction sequence, if you write that down, it'll tell you that that kernel is exactly this thing. Yeah, so we get this. Let me remind you, GK mod inertia, this is just GF. And then now, we just had a whole section about the cohomology of GF. So this is the Frobenius co-invariance of the particle module that's fixed by inertia. And so maybe this motivates the following definition. So anyways, this is like somewhat nice expression. It would be nicer if we didn't have this here. So let's just define a class of things where we don't have that. So say a module M is unramified. If inertia X trivial. And so in this case, the first unramified cohomology of K acting on an unramified module is just the Frobenius invariance of that module. Or if you prefer, it's the same as cohomology of your residue field acting on that module. Are there any questions about the start of this section so far? All right. Just say that these unramified modules actually exist. Maybe relevant to some of Alex's lectures, let's say use an elliptic curve. Let's make it a really nice one. So let's assume it has good reduction. And then also let's fix a prime L different from P. Yeah, then it turns out that in this situation, the L torsion of your elliptic curve is unramified in this sense. Yeah, so if you like spent much time with like elliptic curves in Silverman's book, the main point here is that in this good reduction away from P setting, your L torsion injects when you reduce like modulo your maximal ideal. And so because of that, these points are like more or less the same thing as points defined over your finite field. And certainly inertia doesn't act on the finite field. Finite fields all happen, like with respect to the unramified side of things. More or less why this is true. And so, we can now compute unramified cohomology with all torquing elliptic curve from one perspective is going to be, it's just its Frobenius covariance. Okay, so yeah, it's a nice cohomology computation. Not just so we can compute things not just for finite fields. And now I'm gonna say something about duality. Yeah, so the next few things is gonna be the least motivated part of this talk. Just because there's not enough time to really get into things, but let me at least write down the duality statement and then write down some consequences. Hopefully by the end it won't feel totally okay. So I said this duality is going to be two-dimensional. So some H2s need to show up. This is where they do. For any field F, we'll define its Brauer group to be an H2 with coefficients in units. I guess because we want the Galois action, it should really be units of the separable closure instead of units of F. So now the main thing to try and build some comfort with are the following statements. So the first part of local duality this is really coming from fast field theory, but there's a canonical map. This is the so-called invariant map. I guess really, I would say canonical isomorphism from the Brauer group of a p-adic field onto Q mod C. So many people sometimes write I and B. Okay, so whatever this Brauer group thing is, doesn't matter to us. What we really care to know is that for our local fields, for the p-adic fields at least, it's Q mod C. So this Q mod C is going to be the target of our duality. So let's say for any finite Galois module M, in this setting, M dual, we want to end up in the cohomology. We want to end up in this Brauer group. So instead of taking to Q mod Z, we'll take to this thing. This is units in K bar. Yeah. So now for all n, you get perfect invariant. And the cohomology of our module, between the cohomology of our module, the cohomology of its dual, now set up to land in degree 2. So that's isomorphism. And then you fit H2K, K bar cross, which one tells us is Q mod Z. Yeah, so now the local fields, instead of a one-dimensional duality, we now have this two-dimensional duality. Implicit in this statement is also the claim that these groups both vanish when n is at least 3. So if n is at least 3, then you get some negative thing there, so that got to be 0. So to say that this is a perfect pair, to say that this thing is 0. And then yeah, maybe I can just say, so I set this up for p-adic fields. There's a similar statement one can write down positive characteristic local fields, but then if you want it to be true, you need to smudge things a little bit so let's not worry about that. As if you want it to be like, anyways, you need to modify things a little bit. The other local fields are R and C. There's a very easy duality statement for the cohomology of C. I'll let you all figure that one. For R, its Galois group is just C mod 2Z. And so its cohomology is also easy to understand. And you can phrase this duality statement if you like set things up the correct way. The main cases we care about these p-adic fields. Do you have any questions about just like the statement of this before I continue? Okay. Let me. Yeah, okay, so this statement, sorry, not the statement. So that pairing over there, and like unsurprisingly, it's coming from taking cup products. And because it's landing in H2, maybe the most interesting case is when you cup together two things in H1. So let me remind you like how one actually defines this cup product in this specific case. Yeah, so let me just say like M and N, two Galois modules. And we wanted to find some cup product between their H1s, which at this level of generality will land in H2 of their tensor product. And then there, like M tensor M dual has a natural evaluation map to this k-bar crossing, so then you just push along that to get that thing. So you can define this at the level of co-cycles, so gk to n and psi gk to n. So if you cut these two things together, you should get a 2 co-cycle. So it should take in a pair of Galois elements and spit out something in M tensor N. All right, and then maybe you stare at this and you say, well, that's pretty easy. You just evaluate them and you take their tensor product. If you say this and I say to you, oh no, everything in cohomology is twisted. So you have to remember to multiply by G. And then you're correct. So yeah, so anyways, this duality pairing, this cup product stuff, it's like basically just multiplication, but we're doing cohomology, so you have to remember to twist appropriately. But anyways, you can very explicitly like write down co-cycles representing things. That's a terrible box. So remember this definition of unramified cohomology that was on these two boards. So that'd be great. Yeah, so we have this duality. Anytime you do anything with local fields, you want an unramified version. So it's very natural to ask, how does unramified cohomology behave under this duality? If I put an H2 unramified here and an H2 unramified there, are they dual to each other? Is it something else? Who knows? Soon we'll all know. Okay, so. Okay, so So that duality statement, like I said, just asks that our module be finite. Here we'll want a little more. We want M to be finite. For unramified cohomology to be particularly nice, we'll want our module to be unramified. So this was this property that inertia acts trivial. And there's a new, well, there's a semi-new condition, which is that we want our prime P to not divide the order of our module. So in this like elliptic curve example, this is, we like chose some prime L not equal to G. But if all of these are true, then first of all, one can check that M dual is also unramified. Anyways, maybe this isn't too surprising because M is, but secretly this also needs the second thing. And so once you know this, you have the following commutative diagram where you're interested in how unramified cohomology behaves underneath this cup product. Just 2k bar cross. Well, we know it is definitely erased by now. At the beginning of this section, we computed unramified cohomology of unramified modules. And we saw that it was the same thing as finite field cohomology of that module. So let's work to this. This is isomorphic to this. And here at the level of finite fields, there's also a cut product. So now we have this commutative diagram. But remember, for finite fields, these things have cohomological dimension 1. H2 and higher is 0. So this whole group is 0. I can be more aggressive about this. And so the point here, because these are isomorphisms, commutativity tells you that unramified cohomology is orthogonal to unramified cohomology. So if you pair two unramified classes, you always get 0. Mysteriously, we could write this something like this. And in fact, more is true. So it's not only is it the case that they pair to 0, but they're actually each other's orthogonal complement. You know, anything that pairs to 0 with this whole space must be unramified. I won't say why. If you ask me afterwards, maybe I'll say why, but I won't now. Actually, yeah, wait, yeah, this is great. Alright, so I can extend this elliptic curve example a little bit. You know, anyways, I can give you one consequence of this. That's something obvious. So yeah, so same assumptions. We computed this as this. Right, maybe I should note. So if you're familiar with elliptic curves, maybe you're familiar with this phase pairing between EL and EL. Maybe often you think this is landing inside the roots. Like roots of unity. But if you want, you can think of this as landing inside of K bar cross. So this is some perfect pairing, and so this pairing identifies E dual or EL dual with itself. And so what that means is, yeah, this is a little out of order. EL is its own dual. The unramified cohomology is the orthogonal complement of the unramified cohomology of its dual. So what it's telling you is that this group, this unramified cohomology, is like a maximal isotropic subspace inside of H1KEL. And so in one upshot from this, for everyone in the algebra, if you have some maximal isotropic, then its dimension is half the dimension of the whole space. And so for free, we can compute exactly the dimension of this cohomology group. You know, which I think is something non-obvious to start with. So yes, let me continue. It's twice the dimension of this thing, but this is this. So it's twice the dimension of these Frobenius co-invariants, at least at the level of dimension. These like Frobenius co-invariants have the same dimension as the Frobenius invariants. And okay, the Frobenius invariants, these are just like their fixed points, which is just to say that these are the L torsion points defined over K. So if someone hands you the elliptic curve, probably you can figure out if it has any L torsion or not. And so then for free, you can compute the dimension of this cohomology group, which is something that was very relevant to these like similar groups that we're going to be talking about, / have talked about. I'm supposed to end it at 2:30. All right. Well then, since I have 5 more minutes, let me say one last thing. Yes. Anyway, so that was all about local duality. Anyway, so don't take this last section too seriously. Let me give a taste about what global duality might mean. So for local duality, we need the things landing in this Brouwer group. So maybe, all right, let me just write Q. I could write any number field, but we're just no harm in just reverting back to Q now. So anyways, for global duality, maybe like the Brouwer group of Q will be relevant. And so the first fact, there's another output from class field theory, is that so it's like a global Brouwer class is the same thing as a collection of local Brouwer classes whose invariants sum up to 0. So if you think about what this means, you can get the following things. So let's say let M be a finite Q module and dual homomorphisms. F bar cross. That's Q. F is Q. Good catch. For every place, local duality gives some identification of the cohomology. QV coefficient M with like the 2 minus nth cohomology of the dual thing. So I'm going to keep on writing F's because that's what's in my notes. And then here when I write this asterisk, I mean the like com into Q mod Z version of dual. So yeah, so okay, the duality statement's still over there. So anyways, saying that there's a pairing like that, that's perfect. It's just saying that the left-hand thing is isomorphic to the harms from the right-hand thing at the Q mod Z. And so if one really stares at this for a long time, maybe not that long, I don't know. If one stares at this for a while, eventually they'll realize that one upshot from this is that the following, let's say like 3-term sequence is exact. Maybe if you're, maybe anyways, up to being forgiving about some things. Alright, so what's happening here? If you have a bunch of local classes, then you can pair them with a global class by just doing all the pairings locally, and then you get a bunch of elements in Q mod Z and you add them all up. So that's what this map to the dual is. And then I'm saying, claiming this is exact. That's just saying that if your local classes really like came from one global thing, then when you sum up all these invariants, you get 0. That's exactly this fact. If you have something in the power group of Q, its invariants sum out to 0. So you get some exact sequence like this. And then you can also get there's nothing special about like H1 cross H1, so you can get the same sort of sequence. Where like H0 pairs with H2. So let's do an H2 dual sort of thing. This will also be exact for the same reason. And then you can get a bunch of H2s and have them pair with H0. And this will also be exact for the same reason. At this like H0 level, this first map is definitely injective. And this is, you're just looking at like invariants. So this is like elements of M. So you're just like taking an element M and considering that same element a bunch of times. At the H2 level, this last map is surjective. And actually think about why this is the case. So maybe it's hard and maybe it's not, I don't know. But what is definitely not obvious is that these aren't 3 separate exact sequences. They're actually one 9-term exact sequence. So through these dash maps. Okay, yeah, there are dash maps that connect like this. And so this 9-term exact sequence is what's referred to as global Poitou-Tate duality. Not as nice a statement as that one. But maybe I'll stop there. Oh wait, so the question's like, why is this a K instead of an F?
Yeah, so that here or something like that, like something.
Oh, I think they're the same, if I'm not mistaken. In this like local field setting. I mean, like one way of convincing yourself that like a K is a reasonable thing to put here is that so this E was defined over K to start with. So really, on this EL, there's some action of the entire Galois group GK. But we've said that this is unramified, so this action like factors through. It's definitely mixed by now, but factors through the Galois group of K unramified over K. And so being fixed by Frobenius is the same as being fixed by all of GK. So maybe I convinced you that K is a reasonable thing to put here. But yeah, I also could have put F instead, and still be true.
So I was confused about the title of the talk because usually when people say Poitou-Tate duality, it will mean something like this. So when you say local Poitou-Tate duality, does there carry any meaning?
Yeah, so I would interpret it as this like local duality statement. I guess I was also, anyways, I agree that, usually when I hear Poitou-Tate duality, it's just the global version.
You just mean the local duality.
Yeah. In my defense, I didn't pick the talk title, so you can.
I'm Googling something. Like, I should be local Tate duality, but I think Poitou also studied it. I think I have seen local Poitou-Tate as a description for the local duality.
I see.
I don't think that's why it's possible that I was, I think it would just be local Tate duality.
I have never seen people talking local Poitou-Tate, but it's possible.
Yeah, this is definitely the statement that I was thinking when I
I think there's just no harm in sharing credit. I guess it must be like, because I find it hard to imagine one could prove a statement like this without, also obtaining like the local duality statement.
That's such a good point.
My impression is that Tate and Poitou sort of independently had proofs of this, so they probably also independently had proofs.
I do think local duality goes back a little bit further, but not much.
Okay.
They're all in Tate's Stockholm article, but I think the local ideas were a little bit earlier.
Okay.
But it's confusing.
The global sequence, do you want to restrict the ramification before writing this infinite product? Your map summing up invariance isn't going to be well defined unless you either restrict ramification or make these local classes almost everywhere.
Yeah. So you're right, and this was sort of hidden in my informal / loose. So as I've written here, this isn't literally correct. But if you ever wanted to use this, find an actual reference, and then they would tell you the correct thing. But I think it's somehow maybe if you wanted to have all places, then maybe this should be a restricted direct product where you ask it to be unramified almost everywhere. And maybe this is supposed to be a direct sum, and this is supposed to be something else. Anyways, there's some subtlety in what's actually meant by these three middle terms.